What's up, Algebra 2? Here we are with part 2 of 8.4. Alright, so we did graphing with 1 over x. Then we added in some extra stuff. We were primarily focusing on vertical asymptotes. Then we threw in horizontal asymptotes yesterday. Today we have some special cases, holes in the graph, and slant asymptotes. Okay, holes or points of discontinuity come from when factors cancel out. So if I'm looking at x squared minus 16 over x minus 4, okay, you're kind of jumping to like, oh, vertical asymptote at 4, and the top is bigger by 1, so no horizontal. Alright, let's just see though. Actually, the top, you recognize that. Difference of perfect squares, x minus 4, x plus 4. So, we could actually cancel this out and just graph it like x plus 4. But the original problem that we had, we definitely can't use 4, because in the original problem, 4 minus 4 would have been 0. Okay, so here's what's happening. Because the original problem has this in the denominator, we definitely cannot use 4. But because this does cancel out as you simplify the original problem, it's going to graph just like x plus 4, but we can't use 4. So we can't have 4. Graphs like x plus 4, what would happen if I could use 4? Where would it go? 4 plus 4 is 8. So we're going to have a hole at 4, 8. Okay, we don't have an asymptote anymore because it canceled out, so there's really nothing on the bottom anymore, but because the original problem had that, that's still giving us the issue. So we're going to graph it like it's x plus 4, which is just a line. We're starting at 1, 2, 3, 4, and it's 1x, so I go up 1 over 1, just keeping an eye out for when we get to 4, 8, it's going to be a hole, just a circle. Like when you're doing number lines, and we had like less than versus less than or equal to. The less than was an open circle because it didn't count. It wasn't actually less than, it's just showing you where that part starts. Less than or equal to were the solid dots because it counts, it's part of it. It's the or equal to part. Okay, and this would continue on that way. So we have a line with a hole in it. Don't believe me? Let's graph. Y equals. Let's go with parentheses method this time. Just like to switch it up back and forth so everybody gets a chance to see theirs. X squared minus 16 on the top, divided by parentheses x minus 4 on the bottom. Ta-da! It looks like a line. Mr. Handke, where's the hole in the graph? Trace 4, enter. Can you see that? It says 4, nothing. 4, nothing. Okay? That's why there's a hole. 4 doesn't have a partner. Trace. We got 2 point this, 7, 7.5, 6. We're getting so close to 4. 3.9 is partnered with 7.9. And 4.09 has 8.09, but 4 doesn't have a partner. It's got a hole in the graph. Okay? So, I know that was really quick and the first time you've ever done that, but do you think you can try this one? Go ahead and push pause and give that a shot. Factor out the top, see if anything cancels, and away you go. Hint, hint, something does cancel. Alright, let's see what's going on. With the top, we have x minus 3, x plus 2, over x plus 2. So from the original equation, I know I cannot have negative 2. But here, this part cancels out. And all I have left with is x minus 3. So we're going to start it off just like this, x minus 3. So we're starting off at 1, 2, 3. And our slope is 1, so up 1 over 1, but we know we can't have negative 2. So let's go backwards. Negative 1, down. We can't have anything at negative 2, so we have a hole there. If you want to know the exact coordinates of the hole, you can take what you know you can't have, negative 2, and plug it into the simplified one, the new one, negative 2 minus 3, that's going to be negative 5. So we're going to have a hole at negative 2, negative 5. Okay, and you can use your calculator and check it. A lot of these hole problems are going to be things that cancel out and leave you with a line. Now, it could be crazy and have like x to the third, blah, 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 blah. So, and then x squared, something, something, so that two things cancel out and leave you with a line with two holes. That might be something that happens. Okay, but for the most part, it's just going to be something cancels out and leaves you with a line. You get to some more advanced things, you might have like a parabola on the top or a cubic function on the top with a hole in it, okay? Our other one we have is a slant asymptote, or sometimes called the oblique asymptote. Okay, it happens when the top is bigger by exactly 1. So x squared compared to x to the first. X to the third over x squared. When the top power is bigger by exactly 1, that's when we have the slant asymptote. If the top power is bigger, what do we know from yesterday? Top power is bigger, no horizontal asymptote. But if the top is bigger by 1, we have a slant asymptote. Let's see how those work. Okay, so we have x squared over x plus 1. Alright, so I know I cannot have negative 1. Negative 1 is a no-no. So we draw our vertical asymptote from that. Okay, there's our vertical asymptote. Let's label it. Slant asymptote. Well, horizontal asymptote, question mark? Top is bigger. No horizontal asymptote. Is the top bigger by exactly 1 power? It is. X squared over x to the first. So it is bigger by 1 power. How do you find the slant asymptote then? You're not going to like it. It's long division. This problem's not too bad. The next problem's a little bit worse. Okay, long division. We're taking x plus 1 into x squared, and you have to put 0 placeholders, plus 0x plus 0. Okay? It's not terrible. It's just I know you guys don't like long division, and it's been a while since we did it. So, how many times does x go into x squared? X squared divided by x equals x. And then we multiply it back to the stuff in the front. And we subtract down. That's the tricky part. We subtract everything down. So x squared minus x squared cancels. 0 minus 1, we have negative 1x. And we bring the next spot down. Okay, now we compare the fronts again. Negative 1x divided by x equals negative 1. Multiply it back. And we subtract down. 0 minus negative is actually going to be a plus 1, but we don't have anything left. So that's technically the remainder. Now this is the nice part about it. You get to ignore the remainder. So our slant asymptote comes from the line x minus 1. It would start at negative 1, has a slope of 1, so up 1 over 1. And you can kind of do that slope dot pattern all the way out, because that's going to be your dotted line for your asymptote. Okay, so you can kind of see where our graph's going to go. Let's type it in. Y equals, we're going to use alpha, y equals, go fraction button here. x squared over x plus 1. Alright? You can definitely see where the vertical asymptote is, and you can really see that slant asymptote, how they're both kind of approaching that slanted line. Okay, same as before. We want to have 3 dots, and these are kind of like parabolas, so let's make sure we get that minimum and maximum. So second trace, minimum, left side of it, right side of it, guess in the middle. Okay, now you might be thinking, ew, look at those numbers. 8.23 times e to the negative 7, or e, so capital E means times 10 to the negative 7. That's 0. This is 0. That minimum point there is going to be 0, 0. Okay, so that's 1 dot for the top piece. Let's go with 1 is at 0.5. Can we get a nice one? 2, 3, 4. We're not going to get a nice one, are we? Nope, we're not. Alright, so 2 is like 1.3. 1.3 repeating. And 4 is at 3.2. And this is basically going to go straight up. And this follows it right out. See how that's basically right on the line? Okay? Let's get that bottom piece. Now that's the top, so we're going to need a maximum. So we're going to go second trace maximum. And we'll scooch on over till we get somewhere close. Okay, so left bound, so make sure we're on the left side of it. Right bound, make sure we're on the right side of it. Guess in the middle. Negative 1.999999999, comma negative 4. Okay, use your brain here, folks. It's going to be negative 2, comma negative 4. Negative 1, negative 2. 1, 2, 3, 4. That's the high point. Okay, and we can do a couple. Yeah, we can go a couple points to the left here. Let's go negative 3 is negative 4.5. 1, 2, 3, 4.5. And like negative 5 is negative 6.25. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6.25. See how it's basically right on that line? That was negative 2, comma negative 4.5. No, that was negative 3. This is negative 5, comma negative 6.25. And we know this is going to just near right on down. Okay. This was a tricky one. This is a tricky one for domain and range. Okay, domain. We're going left and right forever. We got that asymptote in the middle. So we have all x's that are not equal to negative 1. The range is a little bit weird because you don't just have a straight horizontal cut, do we? Okay, where are we at? We're at 0. This one gets all the way down to 0 and then up. So this piece, this can be a split range. My y's are greater than or equal to 0. It does get down to 0 and then up, but this piece doesn't go any lower. This piece only gets up to negative 1, negative 2, negative 3, negative 4. It only gets up to negative 4, and the rest of it's below. Less than or equal to negative 4. So we have all those numbers between 0 and negative 4 that the y's won't even use. Pretty crazy. That doesn't happen all that often for you guys. Well, with oblique asymptotes, it probably does. Okay? You probably are going to have some split ranges. And we'll see some more here. With our last one. And I guess with the oblique ones, it might not always ask for domain and range. That might be just more of a horizontal asymptote one. But it's good to think about at least. Okay? X squared minus 1 on the denominator, we can factor that to x minus 1, x plus 1. Okay, that means we'll have vertical asymptotes at 1 and negative 1. So there's our vertical asymptotes at negative 1 and 1. Okay, the top is bigger by 1 power, x to the third compared to x squared. So there's no horizontal asymptote, and there is a slant asymptote because it's exactly 1 bigger. So this one is not the most fun for long division, but it's also not terrible. Okay, remember we need placeholders, so we have x squared plus 0x minus 1 going into x to the third plus 2x squared minus x minus 3. Okay, because it's always going to only happen when it's 1 bigger, it's not going to be very many steps of division. Because if it's 1 bigger, it should always be like just x to the first after you do this first round of division. Okay, so x to the third divided by x squared. Compare the fronts. X to the third divided by x squared should just give me x. We multiply it back. We'll have x to the third. X times 0x is plus 0x squared. X times negative 1, we got minus x. Remember, we subtract down. X to the third minus x to the third, gone. 2x squared minus 0x squared is still 2x squareds. Negative 1 minus negative, so actually plus 1, wipes that out. We have plus 0x. And we bring down the minus 3. How many times is 2x squared, or how many times is x squared going to 2x squared? 2 plus 2. Okay, we have what we need, the slope, the y-intercept. You could multiply this all back and subtract down. This is what we need, x plus 2. So we have the plus 2, and then our slope is up 1 over 1. And reverse it back. Follow that pattern backwards, down, into the left. Okay, so there's your slant asymptote. And that's going to control the outsides. When you have a 3-piece one, left side, middle, right piece, the middle can go crazy. It can do whatever it wants. It's just the far left side and the far right side will have to follow that oblique. The middle one could do some crazy stuff. It might just totally ignore the horizontal asymptote or oblique asymptote. Okay, so you got to definitely take a peek there. This is a long one to type in. But I think it'd be good practice. I mean, if you like the fraction bar and you're using it, go for it. I'm going to use the parentheses again just to keep switching it up every time. So we have x to the third plus 2x squared minus x minus 3 divided by x squared minus 1. Wow. Okay, there you go. We got 3 pieces. And this one does at least appear to follow, like that little slant there, at least does appear to follow the slant asymptote. Okay, so we're going to need 3 pieces, 3 dots on each one. Second trace, we might as well do the maximum on that bottom left. Left side of the graph, or left side of where the maximum is, left side of the hill, right side of the hill, top. So we got negative 1.68, call it negative 1.7, comma negative 0.2. Negative 1.7, negative 0.2, that's the top. Okay, let's see if we can get 2 more points. This is basically going to be straight down, so let's just focus on going to the left here. Negative 2, can we find a nice one? Probably not. No, they're getting worse as we go. Alright, negative 2, comma, negative 0.3, basically right next to it. And then negative 3 is negative 1.125. Negative 3, comma, negative 1.125. These slant asymptote ones, guys, you're going to find out that they get on that slant line in a hurry. Like these are basically right on it. Okay? This middle piece, we're getting kind of tight on time. We're already at 20 minutes, so we're just going to make sure we get the minimum part, and then we're just going to follow the asymptotes. Second trace, minimum, low point. Alright, so here, here-ish, whatever, it's on the top side, and then down here in the middle. Our lowest point there is going to be negative 0.37, negative 0.4, comma, positive 2.8, depending on how close you want to get. If we're just going to go 0.1s on this, negative 0.4, and then 2.8, 2.8. Alright, this is just a crazy one. So it's here, and then it's going to follow over and back up. There's really no other room to get any points. This one doesn't have a high point or a low point. It just kind of goes up and over. So that's going to take care of all your domain or your range. It's going to have all the real numbers for the range just from this branch. So let's see if we can find some nice ones over there. Trace 2, 2, comma 3.6. And again, we are right on that slant line already. And let's just do one more point way over here, like 5 or something. 5, we got 6.95. Let's call it, yeah, let's say 6.9. We don't want to run up to 7. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. It's basically right on that slant line already. And we know this is going to be right here. There you go. These three-piece ones get pretty crazy. Okay? I think we're primarily going to be looking more like that today. Alright? If we're thinking about domain and range, again, we talked about this one is going to cover all the ranges because it goes down forever and up forever on its own. So then we're only going to have limited domain. Can't be -1 or 1. Alright, thanks for watching, guys. Sorry that last one got a little crazy. The video is a little bit longer than we're used to, 23 minutes here. Thanks for watching, and give me a good effort here on this worksheet. Would appreciate it. Thanks, guys.